We're going to begin our discussion of polar coordinates. Just to get started, let me remind you that what we've dealt with in the past and most of our experience in mathematics, we deal with rectangular coordinates, or called the Cartesian coordinate system. And of course, we have a horizontal number line, usually we call this the x-axis, and a vertical number line that we usually call the y-axis, and we move along in rectangular ways. That's and a first coordinate represents a horizontal displacement from the beginning place to the origin, and a vertical, the second coordinate, gives the directed distance, vertical distance, also based on what we just said. But there are other systems. Now, in this case, we're looking at what's called a polar system. And in a polar system, we have a single axis called the polar axis, and it is really a ray. And it starts, now this is laid on top of a rectangular XY coordinate system, but just look at the dot here and the blue line. That is the whole of the polar coordinate system, a polar axis and a pole, of course, and the polar axis is moving along horizontally to the right. Now, the way we indicate a point, as opposed to the rectangular coordinate system where we have an x and a y coordinate, or a first and second coordinate, a polar point is given by two coordinates as well. One is called r and the other is called theta. And we almost read these backwards, because what we do to locate a point, if we have a point in the plane, so let's assume this point, then what we do is we measure the distance to that point from the pole, and we call that r, and we measure the angle from the polar axis, the amount in this case of theta. So the angle that we get measuring from the polar axis and the distance from the pole together give us the point, the description of the point in polar coordinates. That's what we call polar coordinates. Now, for instance, this is as an example, we're given the polar coordinates 2, pi over 4. Remember, 2 represents the r, or the distance the point is from the pole, and pi over 4 represents the angle measured from the polar axis that we need to move along to get to the point. So what we really end up doing, if we were to plot this point, is we look at the angle pi over 4, we measure that angle, we look at the terminal side of that angle, and then we measure 2 units, that r amount, along from the pole along the terminal side of the angle that we get, the pi over 4 angle. And so we locate the point in that fashion. Well, polar coordinates bring up, and they're not difficult to deal with, but they bring up obviously some things that are different than what we're used to. And so we'll begin investigating those on the next page. Well, you can see here we're asked to plot the polar point, -3, 2 pi over 3. And remember, the first coordinate in polar points is an r value, and that's the distance the point is from the pole. And so this brings up an issue, the fact that r is -3. We'll see to that in a moment. And of course, the angle that we measure along is the 2 pi over 3 angle measured from the polar axis. Well, here's the scenario. Here's what we do. First, as I just mentioned a moment ago, the first thing we really do is locate the angle 2 pi over 3. Okay, so we draw that angle. Now here, of course, this blue line is the polar axis, and we measure from the polar axis 2 pi over 3 units, and here is the terminal side of that angle. Okay, initial side, terminal side. Now, normally, if r is a positive value, which would be normal, we would measure along this terminal side in the direction of the terminal side. But if our r value is -3, it means we go in the opposite direction of the terminal side. And so in this case, we're going to go 3 units in the opposite direction. Here's 1. Let's start at the pole. Here's 1, here's 2, here's 3. So that puts us at this point. And this point then is negative 3 comma 2 pi over 3. 2 pi over 3 comes here. We measure in the opposite direction 3 units because of the negative 3. And that's summarized in this statement. When r is negative, you travel in the opposite direction of the terminal side of theta to locate the point. Okay, we're going to breeze through these. We're to plot the points with the following polar coordinates. So let's look at A part. R is 3 and theta is 5 pi over 3. So the first thing we do is locate the angle 5 pi over 3 measured from the horizontal, measured from the polar axis. So 5 pi over 3 actually takes us all the way around. 1 more pi over 3 would be 6 pi over 3, which would be 2 pi, wouldn't it? So we're pi over 3 short. So that's the reason we're going all the way around here to the angle 5 pi over 3. Now the 3, the r value, tells us that we move along the terminal side. Well, this is the terminal side of that angle, so we move 3 units, 1, 2, 3. And so in the plane, that's where this point would be. Now this part B, notice our r is 3 again, but our angle theta is negative pi over 4. So we measure our angle differently, but we still will move in a positive direction along the terminal side of our angle negative pi over 4. Well, of course, negative pi over 4 puts us at this position, doesn't it? So we're traveling for a negative angle, so we travel clockwise rather than counterclockwise pi over 4 units. And then along that terminal side, we measure, whoops, I see that I've got my point labeled wrong here, and that's my bad. I apologize. This should actually be a 2 comma negative pi over 4, because I did measure 2 units along there, not 3, didn't I? If we were to measure 3 units, it would put us at this position, wouldn't it? Pardon me for my mistake. Now, this part C up here, we have r is 3 and theta is 0. Now, we're assuming, and that's the norm is our theta value to be in radian measure. It can be in degree measure, but we prefer in radian measure. And quite frankly, we prefer positive r values as opposed to negative r values, like down here in D, and we prefer, again, our angle theta to be between 0 and 2 pi in a positive direction. So that's what we prefer, but that's not always what we're dealing with. Okay, so let's look at this polar point 3 comma 0. The theta is 0, so that's 0 radians, or it's the same as 0 degrees, isn't it? And so that means that we don't move from the initial side at all. So when we look at our initial side, our angle is 0, so we don't move up, we don't move down at all. We don't rotate counterclockwise or clockwise. So we remain at the initial side and the terminal side are the same. So we measure 3 units along that direction, okay, and it puts us at this point, which would happen to be, if we put this on top of an XY coordinate axis, a Cartesian coordinate axis, we could think of x as being 3 and y as being 0, but in this case the 0 is actually an angle, isn't it? Okay, well, let's look at D part now. And here again we're set up with a situation where we have a negative r value. So that means we're going to go in the opposite direction of the terminal side of the angle pi over 4. So first we locate the angle pi over 4, and then of course the terminal side is right here in this light blue, okay? But we go in the opposite direction of that terminal side 2 units, so we would go 1, 2 units here, and so this is the position of that point, negative 2 comma pi over 4. The polar points are unlike rectangular points. Well, let's go to the next page, and I'll describe what I'm getting at here on the next page. So let's go back to this point 2 comma pi over 4, and of course I've shown it here in this illustration. Our angle pi over 4, and we measure 2 units along that terminal side. Now here's something that's completely different with polar points than rectangular points. With rectangular points, there is only one way we get to a point. There's only one description of a point in rectangular points. I mean, 2 comma 3 means move horizontally 2 units and vertically 3 units. And there's not another way for us to describe that point in rectangular coordinates. But polar coordinates are different because there's more than one angle, if you will, that has the same terminal side as pi over 4. So for instance, as this fades in, it's taking a little longer than I expected. 9 pi over 4 and negative 7 pi over 4 have the same terminal side as pi over 4. I mean, 9 pi over 4, what do? We start on the initial side, and 9 pi over 4 is 8 pi over 4 plus 1 pi over 4, isn't it? 8 pi over 4 is 2 pi, so we go all the way around once to get to 8 pi over 4, and then pi over 4 more gets us to 9 pi over 4, which is exactly the same terminal side. On the other hand, negative 7 pi over 4 would take us all the way around in a negative direction, pi over 4 short of one complete rotation there, okay? And so we could describe the same point using different theta values. Okay, we could use different. So let's look at this. For instance, if we use the theta value pi over 4, 9 pi over 4, we'd go all the way around. Okay, we'd have the same terminal side, and we'd go 2 units along that terminal side. So 2 comma 9 pi over 4 is exactly the same point as 2 comma pi over 4. Likewise, if we measured negative 7 pi over 4, we would get to the same terminal side, and if we move 2 units along that terminal side, we would be at exactly the same location. So this point also is the same. This description of the point, this is the same point as the point we have here and as the point we have here. In fact, there's an infinite number of ways to describe that point, isn't there? We could go around 2 whole revolutions, okay, and then 2 pi over 4. So, I mean, there's all kinds of things that we could do here. In fact, we could even represent the point with a negative 2r value, okay? And the way we would do that is that we would measure an angle that was going to be in the opposite direction of the original terminal side that we had. Here's pi over 4 right here. Well, what would we need to do? We'd need to be pi units more than pi over 4 is one way. So this angle 5 pi over 4 is in exactly the opposite direction of pi over 4. So instead of measuring along the 5 pi over 4 angle, though, we need to go in the opposite direction, so our r value is negative 2. So as you can see, it's a very rich, there's an infinite number of possibilities when we're dealing with polar points the way we describe them. Now, the preferred way, as I mentioned earlier, is to have r positive and to have theta positive and between 0 and 2 pi. In fact, equal to 0 is all right, but less than 2 pi. So 0 less than or equal to theta less than 2 pi is our preference, but we don't always get to deal with our preference. By the way, I hope that you, this is a fairly long video, but I hope you go all the way through it if you're new to polar coordinates and polar equations that we'll talk about in a bit. So please bear with it and spend the time looking at it. It's worthwhile. Okay, let's go to the next page. Now, here is where we put together, and this is very critical for this class and your later calculus classes. This is where we put together the relationship, the connection between polar coordinates and rectangular coordinates. So let's just suppose we have a point, okay, in the plane, and so it's going to, we'll say it's represented by the coordinates x comma y, and we could also represent that point by polar coordinates r comma theta. Now, so let's look at it in terms of x comma y. Then the horizontal measurement would be x units, so that would be along here, wouldn't it? And the vertical measurement would be y units, and so that would be along here. Now, if we're thinking of it as a polar coordinate, then we would measure the angle theta, which would be from the polar axis, which would correspond, if you will, if we laid it on top of the rectangular coordinate system, the polar axis corresponds to the positive x-axis. So we measure theta. Here we get theta. That's that angle that would connect us to this point. And then we measure along that terminal side r units to get to that point. So this distance from the pole is r units. And this angle is theta. Now, just because of the way I've set that up, there's some important observations, because we can think of a right triangle here, can't we? Okay, so if we have a right triangle, then what we know, because of the Pythagorean theorem, that the sum of the squares of the sides is equal to the square of the hypotenuse. So if we take this side of the right triangle, x, and square it, and we add to that this side of the right triangle, y, and square it, then that's got to be equal to the hypotenuse. Usually we say a squared plus b squared is equal to c squared, but our a is x, our b is y, and our c is r. So the is equal to the hypotenuse squared. Now I've written it as r squared is equal to x squared plus y squared. And one thing that we could do here, if we were measuring r as a positive value, then r would be nothing more than the square root of x squared plus y squared. Which means if we knew the rectangular point, then we could calculate the r value of the polar point, couldn't we? Now likewise, because of what we know about right triangle trigonometry, the tangent of an angle in a right triangle is the opposite side divided by the adjacent side. So here the tangent of theta is equal to the opposite side y divided by the opposite side x. Now this is a way for us to determine the value of theta, not directly, but indirectly, as you see here. Now, another important observation is when we bring in dealing with cosines and sines of angles in a right triangle. And the way so let's think of this angle theta as an angle in this right triangle, and the cosine of an angle in a right triangle is adjacent side divided by hypotenuse. The adjacent side is x, the hypotenuse is r, so the cosine of theta is x divided by r. Now if we take that little equation and multiply both sides by r, we'd have r cosine theta is equal to x, or we'll write it as x is equal to r cosine theta. Pardon me, I'm going to clear my throat. Now likewise, the sine of theta is opposite divided by hypotenuse, and in this case the opposite side from theta is y and the hypotenuse is r, so the sine of theta is y over r. And if we multiply both sides here by r, we'll get y is equal to r times sine of theta. Now both of these are critical, which tells us that if we know the polar point, the r value and the theta, then we can calculate the rectangular point by using these two equations. So those, I'm kind of looking at these as two groups of equations. This group helps us take a rectangular point and convert it into a polar. These two help us take a polar point and convert it into a rectangular, which I've summarized down here. That one of the things that we will want to do is convert points from one system to another. And so if we're going from rectangular form, that means we know the x and y, and we want polar form, then what we use is, whoops, I've got that backwards. Oh my goodness. Well, I'm going to have to change something around here. Sorry about that. If we're changing from rectangular form and we want to get to polar form, what that means is we know rectangular form, we know the x and y. So this would help us calculate r. and we'd actually use r is equal to the square root of x squared plus y squared. And we want to know theta, but we do know y and x, and so this would help us determine what theta is if we know y and x. So this is from rectangular to polar. Now, on the other hand, if we were going from polar form to rectangular form, polar form means we know r and theta, and we want to know x and y if we're converting. So we use this, calculate x because we know r and theta, calculate y because we know r and theta. So this is what we would use in that case. In fact, on the next page, we'll do some of that. Okay, so as I was mentioning, we're going to convert from polar points to rectangular points, polar coordinates to rectangular coordinates. Find the rectangular coordinates of the points with the following polar coordinates. Okay, now we're converting from polar to rectangular, which means we need to know the x and y values when we know the r and theta values. And so this is what we're going to use. It's this pair of formulas we're going to use to accomplish that. So let's begin with this first one. And let's remember that the 6 is the r value and the pi over 6 is the theta value. So to calculate x, I just put my r value in for r and my theta value in for theta, of course. And so I've shown that here. X is r times cosine theta. R is 6. Theta is pi over 6. Cosine of pi. Oh, maybe we need to remember the pi over 6 angle's right here, and that has a first coordinate, the square root of 3 over 2, and a second coordinate of 1/2. I hope that you know that by now. Okay. So the cosine of pi over 6 is the square root of 3 over 2, and 6 times, of course, square root of 3 over 2 simplifies to just 3 times the square root of 3. Now, to calculate y, then we're going to use the second formula. Y is equal to r sine of theta. So we replace r with 6 and theta with pi over 6. This time, when we calculate the sine of pi over 6, we get a 1/2. So we have 6 times 1/2 is 3. So the conversion is complete. That is, we've got a shadow there, don't we? The polar point is 6 comma pi over 6. When we convert to rectangular, we have an x value of 3 root 3, comma, a y value of 3. So we have done the conversion. Okay, well, let's look at B here. Once again, we need to recognize that the r value is -4 and the theta value is negative pi over 4. That's not any big deal. And we're going to use to find the x value. That's what we're trying to do, is find x and y for rectangular, aren't we? And so x is going to be calculated using r cosine theta. And so we put a -4 in for r, and we substitute a negative pi over 4 for our theta. Now, again, here I hope that we recognize. Let's look at this. Okay. Whoops. I guess I don't have a sketch here. But you can imagine negative pi over 4 is going to be in the fourth quadrant, isn't it? And the cosine of anything in the fourth quadrant is positive, and so we're going to get a square root of 2 over 2 when we find the cosine of negative pi over 4. So we have -4 times positive square root of 2 over 2, and that simplifies to a -2 root 2. And of course, to calculate y, we'll use y is equal to r sine theta, replace r with -4, theta with negative pi over 4. This time, though, when we take the sine of negative pi over 4, since that's in the fourth quadrant, sine values are negative. So we're going to have a negative square root of 2 over 2, aren't we? A negative times a negative, of course, is positive, and we get 2 root 2. So our conversion is complete. The polar point, -4 comma negative pi over 4, has these rectangular coordinates, -2 root 2 for x, comma 2 root 2 for y. And I've drawn the little diagram over here to just illustrate that this makes sense. This diagram didn't really help me do the calculation, but let's see that it makes sense. If we have a polar point of -4 comma negative pi over 4, then the angle negative pi over 4 is this blue angle, isn't it? And we're going to move 4 units in the opposite direction. So the distance of this red line is 4 units, and it puts us up here in the second quadrant. Well, that makes sense of what we see here. because our x value is negative. This isn't a unit circle, remember, this is 4 units, okay? But our x value is negative, so it puts us over here in the second quadrant, or in the second or third, but our y value is positive, and that makes sense for what we see as this point would look like. So it's at least feasible, and that's what we're dealing with here. Make sure that it's reasonable. Well, on the next page, we're going to change we've been going polar to rectangular, we're going to go rectangular to polar. So as you can see here, we're converting points from rectangular coordinates to polar coordinates. Now, what I've stated here is you will note that it's more involved converting points from rectangular coordinates to polar coordinates because we don't have, here's the reason, we don't have theta is equal to. We have tangent of theta is equal to. Determining the r value, if we know rectangular coordinates x comma y, determining the r value is very simple. Determining the theta value is not so simple, and we'll see some problems that we run into. So our first problem, though, is to find the polar coordinates of the point whose rectangular coordinates are 0, 3. So of course that means the x is 0 and the y is 3, and I hope that we recognize where that is. That's 3 unit. Well, let's do this. These are the steps that we need to take, and it's a little easy to ignore the first step, but it's a critical step. Plot the point x comma y to determine the quadrant or the axis the point lies in or on. Okay, so let's plot the rectangular point 0, 3. Well, there it is. Okay, and the x value is 0, the y value is 3. So there is that point. Well, that's worth a lot to us as we follow along now. Now, the next thing we are to do, though, let's determine the distance r from the origin to the point. We can either use the formula r is equal to the square root of x squared plus y squared, or simply by observation here. What's the distance here? It's 3 units, isn't it? So r is 3. If we use the formula above, r is equal to the square root of x squared plus y squared, then of course x is 0 and y is 3, so we get r is equal to the square root of 9, or r is equal to 3. But in this one case, we could have determined r was 3 just by observation. How far is it from the pole to the point? 3 units. Okay, well, step 3 now is to determine theta. And we can do this by observation, or the formula tangent of theta is pi over 6, is y over x. Now, in this case, if this is where our point is, how do we get to that angle? Well, that angle would be measuring from the positive x-axis, the polar axis, and we would go to where we were vertical. That angle is pi over 2. So by observation, we can tell that theta is pi over 2. So remember, we found out that r is 3 and theta is pi over 2, so we have converted our rectangular point 0, 3 to our polar point where r is 3 and theta is pi over 2. Now, like I said, in this particular case, the graph helped us do this pretty easily. If we would have tried to do something other than by observation to determine theta, let me point out that why we have problems. If we tried to calculate theta by using the formula tangent of theta is y over x, well, the problem we'd run into right away is y is 3 and x is 0. And of course, that's an issue, isn't it? That's not a defined fraction. And so we have a problem using the formula in this case. And we also have the problem in other cases that we'll see in the next example. Well, actually, I think I misspoke. In this next problem, it goes fairly smoothly, I think, but let's get started. Find the polar coordinates of the rectangular point 2, -2. So remember, step 1 is to plot the point in rectangular coordinate system. And so just a quick sketch, and obviously this is a pretty good sketch, but usually I just have a real quick sketch by hand. And so our point has an x value of 2 and a y value of -2, so that's our point. The job, of course, is to figure out what theta and r are. Okay, the values of r and the value of theta. Well, anyway, the step 2 is to calculate r, and that's pretty easy when we know x and y, okay, because r is the square root of x squared plus y squared. And so in this case, that's the square root of 2 squared plus a -2 squared, or the square root of 4 plus 4. Of course, that's the square root of 8. And we should simplify the radicals. And so when we simplify the radical as much as we can, square root of 8 ends up being 2 times the square root of 2. So now we know the r value. Now our next job is to determine theta. And we can't look at this as easily and be sure of what theta is. We might be able to make a pretty good guess here. You know, I'm thinking actually theta might be -pi/4 because these two coordinates are the same. But let's see. In fact, that's what I said, isn't it? By observation, I think we could decide that theta was -pi/4, or if we wanted a positive theta, it would be positive 7pi/4. But if we use our formula, that is, using tangent of theta is equal to y over x, then we would have tangent of theta is -2 divided by +2. Y is -2, x is +2. And of course, that simplifies to -1. And so to calculate theta, we would say, well, it's the inverse tangent of -1, and we would get a -pi/4. Now, I need to make another point about this, but here's what we've got so far. We found our r value is 2√2, and we found at least one way we could determine this is we could use -pi/4 as our angle. Now let's remember the inverse tangent is always going to give a result that's between -pi/2 and +pi/2. So we were lucky in this case that our angle happened to be in the fourth quadrant. That's why, and actually negative angle, okay? And so that's why we were fortunate enough to say we could use the inverse tangent function here. You may not know what I'm talking about, but the next problem will certainly illustrate it. You notice I've marked out find the polar coordinates of the rectangular point -1, -square root of 3. And of course, I've marked that out because there's multiple ways we can describe an angle, polar point. So I shouldn't say the necessarily. But my preference is to have a positive r and a positive theta that lies between, that's my preference, lies between 0 and 2 pi. In the last example, it was easiest to use a negative angle for theta, wasn't it? Okay, well, we go about our business, and the first thing to do is to plot the point. And so, you know, this really the issue here, more than anything else, is that this point is in the third quadrant. That's really the issue, okay? Let's just keep that in mind as we move through. Okay, the second step, of course, is to calculate r, and that's always easy to do, and there's no issue involved except we have to deal with the algebra and we have to deal with the simplification of radicals. Since x is -1, we have r as the square root of x squared plus y squared, so r is the square root of a -1 squared plus a negative square root of 3 being squared. Of course, when we square -1, we get +1. When we square -√3, we get positive, and when we square √3, we just get 3. So we have the square root of 1 plus 3, or square root of 4, which is just 2. And so calculating r is always easy. It's calculating theta, determining theta, that we have trouble with. Now, let me run back up here. Our theta is not between -pi/2 and +pi/2, is it? Our theta is some big angle greater than pi. Okay, so since the point is in the quadrant, and that should say quadrant 3, not quadrant 2, I'm sorry for another mistake. Okay, since the point is in quadrant 3, then theta cannot be the inverse tangent of y over x. I mean, we say tangent of theta is y over x, but the inverse tangent is always going to give a result between negative pi over 2 and positive pi over 2. And so theta is not going to be the inverse tangent. There is the problem. Okay, that's an issue. Now, just as I said, why is that the case? Well, because the inverse tangent of anything is always between negative pi over 2 and positive pi over 2. So what we're going to do here is we're going to be a little bit ingenious. We're going to find theta, we're going to find the inverse tangent of y over x. But the inverse tangent of y over x is actually going to give us some angle up here, I believe. And so we need to take that angle and adjust it so that we're dealing with the angle we see. Okay, well, and I'm calling that angle alpha. So I'm going to call alpha, because I know it can't be the theta value. Alpha is the inverse tangent of y over x. And of course, in this case, y is negative root 3 and x is negative 1. And so this is the inverse tangent of just root 3. And that happens to be, using my calculator, that happens to be pi over 3. Okay, well, that's what I was saying. Pi over 3 is actually this angle, isn't it? See, that's this angle. Let's see if I've got a little diagram here. Oh, there's my diagram. I didn't. Okay, so pi over 3 is this angle, and so theta is that alpha pi over 3 plus pi units more. See, it's pi units more right here. Okay, and so we're going to take alpha and add pi to it. And alpha being pi over 3 plus pi ends up being 4 pi over 3. So this angle is 4 pi over 3, which makes sense now of where that resides. Okay, so now we can do our conversion. The original point in rectangular coordinates here, we calculated r without a hitch, and we found theta by knowing it wasn't pi over 3, it had to be pi units more than that. And that's how we got theta to be 4 pi over 3. Okay, and again, we knew that it couldn't be pi over 3 because of where the angle is rectangularly. I mean, where the point is rectangularly. You can see here that we're changing from converting points from one system to the other to converting equations. I mean, a rectangular equation is the type that we're used to seeing, and we're going to convert equations from one system to the other. So instead of having x's and y's, r's and thetas, or vice versa, instead of having r's and thetas, we'll have x and y's. So our very first problem in this idea is we're going to convert from a rectangular equation to a polar equation. So our rectangular equation is 3x squared plus 3y squared is equal to 2x. And so we want to convert this to polar form. So the very first thing to realize, this is simple, okay, generally. I guess I should qualify it. It's simple generally because we have these relationships that x is r cosine theta and y is r sine theta. And so anytime we see an x, we can replace it with r cosine theta. And anytime we see a y, we can replace it with r sine theta. So we can get rid of all the x's and all the y's and just have r's and thetas left over. So it's simple. Now, if you recall the problems we were just looking at, taking a rectangular point and converting it to polar form was rather difficult. But taking a rectangular equation and converting it to a polar equation is relatively simple. Now, what we saw previously also is taking a polar point and converting it to a rectangular point was simple. We'll find out that taking a polar equation and converting it to a rectangular equation is a little more challenging. We have to be more creative. But here it's pretty straightforward. So we'll start with our equation, okay? And then we just replace each x with r cosine theta, each y with r sine theta, and of course x with r cosine theta. And then we just do the appropriate algebra. When we square r cosine theta, of course, we get r squared cosine squared theta. And when we square r sine theta, of course, we get r squared sine squared theta. And of course, this wasn't squared here. So now we take this equation. Now here would be the challenging part, is that we want to simplify this as much as possible, and eventually we like to solve it for r. Like normally with rectangular equations, we like to say y is equal to. Sometimes we can't easily, like here. If we can say r is equal to, that's our preference, but we certainly want to simplify. And I'm noticing on this left side, I have a common factor of 3r squared, and so I'll factor that out. Now that's significant, because when I factor 3r squared out, it leaves cosine squared theta plus sine squared theta. And it's an important observation to recognize that's just 1. So this side is really 3r squared times 1. Okay, so it's just 3r squared equal to 2r cosine theta. Well, we've simplified a lot, haven't we? Now, another thing that we could do at this point is that we could divide both sides by 3r. And if we did, we would get 2 over 3, and r over r is 1, so we could get 2/3 cosine theta. So we've solved this for r by this last step, haven't we? But we could have actually been correct if we would have left it in this form, and maybe that's a good form to leave it in, but that's not what we did here. Okay. Now I want to point out, as we are looking at this problem, that there is an alternative method. There's an alternate to what I did. And that alternate is that I could have noticed in my original equation on the left side I have a common factor of 3. And if I factor 3 out, of course, I have 3 times x squared plus y squared. And then I observe that since r squared is x squared plus y squared, in place of this x squared plus y squared, I can just put my r squared. And of course, we still need to know that x can be replaced with r cosine theta, which I've done here. And so you see that we get to the same position just a little differently. Either one would be correct. We'll continue to convert from rectangular to polar, just to show a little different issue here. And by the way, here's our the equation. 3x minus y plus 2 is equal to 0. We're converting this rectangular equation to polar form. But while we're looking at this, just to point out to you that this is actually the equation of a line, isn't it? If we added y to both sides, we'd have y is equal to 3x plus 2. So this is just the equation of a line. Let's see what this would look like in polar form. So we take our equation, and remember, when we're converting, it's very simple to do when we're converting from rectangular equations to polar equations. We have an easy replacement for all of our x's and y's. Okay, so we'll just go straight forward and we'll do that replacement. For x, we put in 3 cosine theta, and for y, we put in r sine theta. And so after the first step, it looks this way, and I just took out the parentheses. Parentheses were for emphasis only. But now here's the issue, is that we want to simplify and solve for r if possible. And this requires us being proficient in algebra. Here's what I'm noticing. Okay, let me just show you above. I'm noticing these two terms. When you're solving for r, the common thing to, or a variable, the common thing to do is get all terms involving that variable on one side and any term not involving the variable on the other side. So since 2 doesn't involve an r, I subtracted 2 from each side. Now the left side, both terms have an r in them. And the significance of that, if both terms have an r in them, then r is a common factor that can be factored out. So now I've factored r from both of these terms, leaving r times 3 cosine theta minus sine theta. Well, if I want to get r alone now, I can divide this term out, this factor out. This is kind of like r times 5, or 5r. If I wanted to know what r is, I divide out that factor, don't I? And so I'm going to divide on both sides by 3 cosine theta minus sine theta. And when I divide on the left, I'm left with r. When I divide on the right, I'm left with negative 2 divided by 3 cosine theta minus sine theta. So as this is what we were after, but just to remind you that this is the equation of a line, and this is the equation of that same line in polar coordinates. This, I guess, looks a little more complicated, doesn't it? But nevertheless, that's what it is. Well, on the next page, we're going to change from converting from rectangular to polar to vice versa, that is, polar to rectangular. So here we have a polar equation. R is equal to negative 8 cosine theta, and we're going to convert from this polar form to rectangular form. So an equation that has x's and y's in it, and no r's and thetas. Now, whenever in doing this, as I said, is more difficult than what we've been doing. I mentioned that when we were going from rectangular to polar equations. We have to sometimes be very creative here, because we don't have a direct replacement for r in terms of x and y, and we don't have a direct, not a good one, square root of x squared plus y squared, no. And we certainly don't have a good replacement for theta or cosine theta in terms of x's and y's. So what we're trying to do usually when we're going from polar to rectangular, we're trying to create situations where we have an r cosine theta that could be replaced with x, or an r sine theta that could be replaced with y. So that's how we get x's and y's, is with r cosine thetas and r sine thetas. Now, on occasion, we try to, I see that I've left off an e there. I've got all kinds of errors in this video, don't I? Sometimes we try to create an r squared, and an r squared we can replace by x squared plus y squared. So that's another way we can introduce x's and y's. Well, let's take our equation that we have here, r equal negative 8 cosine theta. Now, to tell you the truth, I'm looking at this cosine theta, and I'm thinking it'd be nice to have an r cosine theta so I could put an x right there. And the way I could do that is I could multiply this side by an r. If I multiply the right side by an r, I'll have a negative 8 times an r times a cosine theta. But then I'll have to multiply the left side by r as well. So I'm showing multiplying both sides by r to create the r cosine theta that I wanted to do. Now, as I simplify that, I get kind of an extra benefit here, don't I? Because this side will be r squared, and this side will be negative 8 times r cosine theta. So I'm fortunate here that I can replace r squared with x squared plus y squared, and of course r cosine theta can be replaced with x. So you see I have an equation that's x squared plus y squared equal negative 8x. Now, because we have a y squared, we can't easily solve this for y, so we would not even try. And the truth is, in our homework, we may be done with the conversion, but sometimes our homework is going to expect us to recognize more. And what I would like you to do is to recognize that this is the equation of a circle. Okay, this is the equation of a circle, and it may not be clear to us. Let me show you. Okay, remember what circles look like in general. X minus h the quantity squared plus y minus k the quantity squared is equal to r squared. If I added 8x to both sides and got my equation to look like this, and I took these first two terms, x squared plus 8x, we did this in the earlier part of the semester, and completed the square. Now, remember, how do we complete the square? We'd take that 8, okay, and we'd divide it by 2, which would give us a 4, and then we'd take that 4 and we'd square it, which would give us a 16. So we need to put a plus 16 right in here. Now, we put a plus 16 on the left side, we got to put a plus 16 on the right side. Then, this should factor in a special way. And the way would be x plus 4, we remember that, the quantity squared. That's what this trinomial will factor to. Now, I don't really need to write y squared as y minus 0, but I did that for the next step, because now we can tell that not only is this a circle, we know the center is negative 4 comma 0, and the radius squared 16, so the radius is 4. So we did, in fact, have a circle. Okay, first, this rectangular equation is that of a circle, which means this polar equation is that of a circle, and it's actually a pretty simple equation for that of a circle. Well, okay. I think I have one more problem I'd like us to look at. Remember, before we move to the next page, what's stated here. When we're going from polar to rectangular, sometimes we have to be very clever. And I'm not giving very many examples, but we do have to be clever occasionally. And usually we're trying to create r cosine thetas or r sine thetas by maybe multiplying both sides by r, or some power of r, in fact. Sometimes we try to create an r squared so that we can replace that with an x squared plus y squared. Let's just keep that in mind as we move to the next problem. We're to convert the equation r equal 5 from polar to rectangular form. Now, this doesn't have anything to do directly with this problem, but I'm just like to point out that this is a degenerate type of equation. Like in a rectangular form, the equation x equal 3 is a vertical line, isn't it? And the equation y equal -4 is a horizontal line. Well, r equal 5 is degenerate in the fact that it just has one of the two variables. It doesn't have a theta at all. So theta can be anything, but r always has to be 5. Now, if r always has to be 5, but we can have any theta at any angle, just imagine, okay, what that might look like. And I think it will become obvious in a moment. Now, since we don't have any cosine thetas or sine thetas, multiplying both sides by r isn't going to help us any, is it? I mean, we're not creating, multiplying both sides by r, we're not creating an r cosine theta or an r sine theta, since they don't appear in the equation at all. All it does is give us r squared is equal to 5r, which is x squared plus y squared is equal to 5r, but we still don't have a way to replace r. So we take a different path. And the different path is we're going to try to create r squared, not by multiplying both sides by r and introducing an extra r over here. We'll just square this side and square this side. And that way we won't have any extra r's, will we? So we're going to square both sides. And when we square the left, we get r squared. When we square the right, we get 25. And now we can replace r squared with x squared plus y squared. And then we notice x squared plus y squared equal 25 is also a circle. It's a circle whose center is the origin and whose radius is 5. Center at the origin and radius is 5. And if we would have thought way back up here, we don't care what theta is. It can be anything from 0 to 2 pi. It can be everything in between. The radius, the r, just has to be 5. So for no matter what angle we're at, we go 5 units from the pole. And so that, in fact, is exactly what a circle is. Some set of points that are the same distance from the origin, or in this case, the pole. Or the same distance from the center. In this case, the center is the origin or the pole. So we've completed it in using a little different technique here. Well, you'll be doing a lot of different types of problems, conversion of points, conversion of equations, and once in a while you have to be creative and careful, of course, when you're converting points, as we said before. If you're converting from rectangular to polar, we have to be careful with the tangent of theta idea. And when we're converting equations from polar to rectangular, we have to be creative to get our cosine thetas, our sine thetas, or r squareds. Good luck to you.